Hello there, this is Coach Ikram, and welcome to this video on Hess's Law. So Hess's Law was discovered by a French chemist, Germain Henri Hess, who found that the enthalpy change, or change in H, in a reaction is going to be the same whether or not your reaction occurs in one step or it occurs in many steps. Overall, that enthalpy will be the same. Most reactions will take more than one step before they're completed. So to sum that up, the change in enthalpy of the whole reaction is going to be the sum of all the enthalpies for each subreaction that it goes through before it's completed. So what we're going to do is we're going to solve for enthalpy using this law and this concept. And what you may have to do is, looking at all the subreactions, you might need to reverse a reaction. And therefore, you change your enthalpy sign of that subreaction. You might need to multiply a reaction by a common factor. That could be a whole number, that could be a fraction, in order to overall calculate your value for delta H. Let's jump right in and do an example. It says, given the following reactions and their enthalpy changes, calculate delta H for the following reaction. So you see we've got my overall primary reaction right here. And this is the reaction that we are trying to find the enthalpy for. We don't have it, but we do have these three subreactions that it goes through, and we do have the enthalpy for those. So what I like to do is I like to start with one of the entities in the primary reaction and find it in the subreactions, and then manipulate each equation accordingly. So for example, the sulfuric acid, H2SO4, I'm going to go find it in my lower subreactions. So it's right here in this reaction. If you notice, I don't need to multiply this equation by anything. It's the same mole. It's 1 mole of H2SO4. But the H2SO4 in my subreaction is on the right-hand side. It's a product. And the H2SO4 in my primary reaction is a reactant, which is a bit of a problem. So what I'm going to need to do is reverse. I'm going to put an R here. I'm going to reverse this first equation. And I'm going to go ahead and rewrite it down below so you can see exactly what I'm talking about. Now we're going to make H2SO4 my reactant, and I'm going to have H2S plus 2O2 as my products. And my change in H now, it was negative 235.5 kilojoules. That was originally an exothermic reaction, but if I do the reverse of it, I have to change the sign for my change in enthalpy. So now it's going to be a positive. I'm going to actually put a positive there to show you 235.5 kilojoules. So now let's talk about the next entity we've got. We've got SO3 right here. If I go down and find SO3, SO3 is written right here. It is the correct number of moles, it's 1. And it's also on the right side of the equation. It's a product, just like it is in my primary reaction. So this is going to be A-OK. And I'm actually going to go off and cross this one out because we have rewritten it below, so it's easier for you to see. My third entity is the H2O gas. I'm going to go ahead and find it. Note that I've noted the phase changes, or the phases, sorry, for the water down below. We've got a liquid and a gas. So what I'm looking for is this gas, steam. I find it right here. It's also on the correct side. It's a product. It's also got 1 mole, which is what it needs. So that is also perfectly good. And I'm ready to go. So now I'm just going to show you the concept behind this, how this ends up working out to give me my final equation. So I'm going to write down, if these 3 subreactions all take place, I'm going to write down all of my reactants for these 3 subreactions and then have all of my products so I can show you how this works out. So if I write down every single one of my reactants, I'm going to have H2S, 2O2, plus H2O, plus 2SO4. And all of my products And so now what I can do is I can actually go through, and just like I did when I did net ionic equations, I can cancel off the entities that are on both sides, my products and reactants that are on both sides. So I'm going to go ahead and change my color pen here so you can see it easily what I'm doing. So I've got H2S over here, and I also have it over here, so that can be canceled off. I've got 2 O2s here, and I've got 2 O2s over here now. And I've got H2O liquid, I should have had a liquid here, right here and right here. And so you'll see what I'm left with here. Let's go ahead and write purple. I've got this piece, this one, and this one. And if I rewrite that, you'll notice, you will notice that that is my primary equation that I have up here at the top. That's exactly what I was looking for. So in manipulating those three subreactions, I end up with what I'm looking for. So now to find my total enthalpy, Hess's law states that my total enthalpy for that primary reaction is going to be the same as the sum of all my subreactions. So these three are my subreactions. I'm going to add those up, the negative 207 plus 44 plus 235.5. And with sig figs, I'm going to get a negative 73 kilojoules. And that is my enthalpy for that primary reaction. Let's go ahead and do one more example. So in this case, we've got nitrogen gas reacting with 5 moles of oxygen gas to form 2 moles of dinitrogen pentoxide. So I'm going to start with my 2 and 2 here. I'm going to find it down below, and if you'll note, I found it right here. It is a reactant, so it's on the right side of the equation that it needs to be on. However, there's only 1 mole of it in my sub reaction. So what I'm going to need to do is times this entire piece by 2. And so what this is going to end up becoming is a positive 362 kilojoules. So this becomes, when I times it by 2, it's going to become a positive 362 kilojoules. I'm just going to go ahead and write that off to the side. Now I'm going to look for my oxygens. And if you notice, I've got oxygens everywhere. I've got one here, here, here. If you are looking for a reactant or a product that's found in more than one place, the general rule of thumb is to always leave it for the end. Because what you'll find is it'll either work itself out or you'll be able to manipulate one of the equations in order to get what you need. So I'm going to go ahead and leave that for now. I'm going to focus on this dinitrogen pentoxide. I've got 2 moles of it up here. If I come find it down here, I've got 2 moles of it right here. And those 2 moles are on the correct side of the equation. They're both products. So this is actually good to go. I don't need to manipulate that middle equation. So now that leaves me with my oxygen. So I'm going to go through, and what I want is 5 oxygens on my reactant side overall if I was to rewrite all these equations. So because I've times this by 2, what I've got now is let me change my pen color for you. I've got 2 oxygens here, plus 1, plus 1. So right now I've got 4 oxygens total on my reactant side. I need to manipulate one of those equations in order to get the 5 oxygens I need. I don't want to manipulate those bottom 2 equations because I've already done something with them. And if I mess with them more, I'm going to mess up what I just did. So I'm going to go ahead and mess with this top one. And I'm going to go ahead and times this one by 2 as well. And so when I times this one by 2, I'm going to end up with 2 oxygens here. This will be a 4, and this will be a 4. And that means I also have to times this value up here, my enthalpy, by 2 as well. So when I double this, it's going to be a negative 228 kilojoules. So now I've manipulated all my equations. I've got 3 values that I need to add up. This one, and this one. So when I go ahead and total that, my sum enthalpy for my given reaction is going to be a positive 24 kilojoules. So overall, this is going to be an endothermic reaction. All right, that is the last slide for this section of notes. Make sure you've taken good notes and come to class with questions.